In this video, you are going to take a look at the uncertainty that come with the measurement. In the previous video, you're looking at the number and unit. So this one, we are going to add the error or the uncertainty to that come with the measurement. So this one is going to be how you are going to report your number when you do some measurement in the lab. Okay, so before we get into everything else, so let's actually looking at first what type of things that will have the error that come with it. Okay, so let's take a look at the first example. Okay, so this one we have the package of candies. Okay, so we have candies inside this package here. And if you're looking at this, right, so if you count how many of them, you can count, right? So 1, 2, 3, 4, 5, right? So you see that there are 5 candies in this package, right? So you just count them. Okay. So now what about how many inches are in 1 foot? Well, you know also that there are 12 inches, right? That is equal to 1 foot. So these two you know. Now what about if I give you a pencil and I ask you to measure the length, right, from eraser to like the tip of the pencil, right? So here, in this case, what would be the length of this pencil, right? So some might say that, oh, it's 7.5. Some might say that, oh, it's not exactly 7.5, it's 7.51 or 7.548, right? So on, right? So, and then you report with the unit, right? So you probably notice that the last one that we measure, right? We measure the length. You can actually, the accepted value can be several, right? So it's not exact, it's not going to be exact value. It's going to be the range of the acceptable values. So therefore, in this case, this is what we are going to learn, right? So the error that come with that, right? So in this case, you probably notice that the first two that we count when we define something, those are what we call exact number. Okay, so for example, as you already see, right, when you count the discrete objects such as the candies or apples, right, those number are going to be exact value or what we call exact number. Another one that considered to be exact number would be the defined quantities, such as we define that there are 12 inches equal to 1 foot. So therefore, in this case, the 12 is the exact number, not approximated, right? So same thing when we define that 1 inch equal to 2.54 centimeter, the number 2.54 centimeter or that number right there would be the exact number. We did not approximate it. And the last one, the number that is part of the equation, such as in this case, like in radius, right? So it is equal to half of diameter. So that number 2 right there is the exact number. Okay, so however, if you're looking at something that you measure out, such as in this case right here, when we're measuring mass of a sample, okay, so the number that the digital balance give you, 21.427, this one is not exact number. This going to be the number that contain uncertainty as well. And it's turned out that the last digit, okay, so that would be the digit that we are uncertain. Okay, so we estimate it. Okay, so that would be the last digit. So that means in this case, the first 4, those are the certain value, and the last one is what we estimate. So that means anything that we measure or come from the measurement, you need to know that the last digit is going to be the uncertain digit, or the digit that we estimate is always going to be present at the last digit. So that means in this case, when we report the measurement of this, is going to be whatever that you read, right? And then plus minus the error. So let's say like this balance giving us that the error for this is going to be 0.005, right? So that means that part right there is what we call uncertainty. So that means the acceptable value would be within the range of plus minus 0.005. That's what it means. Okay, so anything between that, right? Those are acceptable value. Okay. How do we know what would be the value of the error here? So this is when you will need to look up the value that report on a device, because every device, the lab device, would be calibrated already, right? So, and they are going to report the error or uncertainty within that as well. So you can actually look it up from the manual, right? The device manual, or sometimes it might say it on the glassware on the device itself as well. So now let's go back to the same example that I mentioned before, which is measuring the length of the pencil. Okay, so I'm going to give you several type ruler, and we are going to look at how can we report this. Okay, so in this case, in order to report this, we need to find out, right, the certain digit. Okay, so we know that according to this, we know that the certain digit would be 6.5. So that means what we certain so far is that is right around the mark. So that means what we certain is 6.5, right? 0.5 what? 0.5 something. We don't know what that is. So that means in this case, you will need to make one more estimation to actually give us the correct number of uncertainty. So that means in this case, you probably notice as well that it was not right at the mark. It's kind of like a little bit beyond that, but not much, right? So I'm just gonna give it 6.51, for example. Some people might be like, hey, but I see it right at the mark. How should I report that? Well, in this case, you're just going to report it as 6.5, and then you are going to add one more digit, which is 0. So that means in this case, 0 and 1, those are the estimate digit, and those are going to have to be included in the reading value. Okay, so some of you might be like, hey, I don't agree with you. What about, I see it as 6.52. Is that correct? Yes, it's correct, right? So all of these are acceptable value, right? So it's within the range, right? So that means in this case, to report this, all you have to do is you are going to do read 6.5 and then do one more estimate and then add those as uncertainty. So you probably notice that in this case, right? So this plus minus 0.02 right here is going to cover those range already. Okay, so that would be the uncertainty. Okay. All right, so that means the actual length of this pencil is going to be between that value, right? 6.49 and any between that 6.09 and 6.55 would be acceptable value for this reading. Please note that whenever that you deal with measurement, is always going to come with the uncertainty in the last digit. Okay, so your last digit always going to be the digit that is estimate. Okay, so it's going to need to be included within that reading of the measurement. Okay, so the number of the digit, both certain and the one that you estimate, all of these together is what we refer as significant figures. Okay, so that means in this case, the number of significant figures, it would tell us, right, how certain we are, right? So it's because the first part is tell us about the certainty, right? Like the certain of the number, and the last digit is what we estimate. So now let's take a look at the difference between the two measurements here. Okay, so the first one, we are going to use the ruler that has only mark on each of these number right here. The second ruler has marked that is increment by 0.1, right? So we are going to see all of those. So let's take a look at the first one. How would we read this? Okay, the first one, we're certain that the pencil is going to be between 6 and 7, right? So we're certain it's already at 6. So I'm going to read that. Okay, so I'm going to read that is 6, and then we are going to estimate one more digit. But the reason why we need to estimate one more because we don't know, right? So this part right here is something that we are not certain. So my report would be 6.6. So the estimated digit would be in the second place. Okay, so this digit right here would be the one that we estimate because we are uncertain because there is no mark tell us what it is, right? All right, so the next one, okay, so this one, if you're looking at this, you probably notice that what we certain for sure is going to be up to 2 digits, right? So 6.5. So let's say it's 6.5. And then we're not sure what is one more, then you need to report another one. It can be like 0.55, 0.54, and so on. So that means in this case, the estimated digit would be in the third place. You notice that the first reading, right, give you only 2 digits, which is going to equal to like less number of significant figures than the second reading because contain 3 digits. So in this case, we can say that the second ruler give you more significant figures. The more significant figures or sig fig, you are going to know that that measurement is going to be more certain. Okay, so it's going to give you a greater certainty of the measurement. Okay, so that means in this case, the second ruler would be more certain than the first. All right, so what about how to count number of sig fig, right? So you kind of like know that approximately already. So note that this one is going to be based on pretty much note that the last digit is going to be estimate digit always, that we always count towards sig fig, right? So according to what we see before, because you count everything, right? You count both certain and uncertain. So that means in this case, when you deal with the 0 before or 0 after a non-zero digit, right? You are going to pretty much based on this, okay? So this is the rule. So I'm going to apply this rule and with the example, so that way it's easier for you to understand. Okay, so for example, if you are given non-zero digit, okay, so if the number contain no zero, right, so you are going to count every one of those to be significant. So therefore, the number of sig fig here would be 5 sig fig. Okay, the zero between the non-zero digit. Okay, so this is always going to be significant. Okay, so these 2 zero will always be significant if it's between two non-zero digit. Makes sense, right? Because we know that the last digit is the uncertain, is part of the sig fig. So therefore, everything else that comes before that, right, is have to be significant, right? So it's going to be the uncertain, right? So in this case, we have 5 sig fig. Now, the one that contain the leading zero, okay, so this leading zero is going to be what we call a placeholder. The reason for that is because you already learned, right, that this decimal form can be reported as scientific notation. So if you convert this into scientific notation, 7.56 times 10 to negative 3, you see that this zero right here disappear because it's already become the notation. So therefore, in this case, what you are going to count is going to be only the non-zero digit right here, right? So that's what left. So therefore, in this case, you are going to end up with only 3 sig fig. Okay, so this is going to equal to 3 sig fig. Okay, because we don't count the first 3 zero because they are placeholder, right? It's represent the notation, right? So the scientific the notation here will not count as part of sig fig as well. Okay, now you may ask me, hey, what about if I put 0.00756, and what if I put 0 here? Well, same thing here. You can do the same thing. Convert this into scientific notation. It might be easier for you to see. Right, so if you convert this, it would be 7.56. Don't forget, remember the last digit is the estimate. So that means you need to include that, right? Because it's going to be included in the measurement, but you need to include the estimate digit, right? So, and then times 10 to negative 3. So therefore, in this case, you are going to count that last zero right there. So therefore would be 4 sig fig. All right, so let's take a look at next example. What about this one? Okay, so how many sig fig here? Same thing, right? So you can do scientific notation and count, right? So in this case, you probably notice that the leading zero, these are the placeholder. We don't count them. We only count the last 3. So therefore, they are 3 sig fig. This one, again, so these 0 are between the non-zero digits. So those are significant. The last 2 zero also significant as well, because it's come after the non-zero digit, right? So so this one total would be 7 sig fig. What about 700, right? So this one doesn't have decimal point, but these contain decimal point, so you can actually put it in scientific notation to count before you count the number of sig fig, right? So it's relatively easy. This one is turned out to be ambiguous. The reason for that is because there is no decimal point for us. So if you want to make it clear, you need to actually put a decimal point. Okay, so you can put it either after 7 and convert that to scientific notation so that you can say that this is 3 sig fig, or you can put a decimal point at 0, the last 0, to make sure that, oh, this is what we include, right? We include all of this, right? So so in this case, it's indicate that the decimal point indicate that the last 0 is the estimate digit. Okay, so total would be 3 sig fig. Okay, and again, so as I mentioned before, the one that come with the scientific notation, right? So you only count the number, not the exponent, right? So not the exponent part. Okay, so in this case, this come out to be 4. Okay, so this would be 4 sig fig. I would like you to complete the DIY problem here. Okay, so make sure that you complete all of this first before you resume the video again. Okay, so when you get all the answer, when you're ready, then resume the video again. All right, here are the answers. Okay, so if your answer are not the same as what I have, please do not hesitate to reach out to me. Okay, so I'm here to help you. Next, we are going to take a look at sig fig in calculation, because when we do some measurements such as density, right? So when you measure mass and measure volume, right, you need to divide them up, right? So we need to figure out how many sig fig would be in your final answer. Okay, so the rule for calculations can be broken down into 2. One is for multiplication and division, and the other one is for addition and subtraction. So these 2 are not going to be the same. Okay, so I'm going to walk you through what would this be? Okay, so the second one is that you are going to need to know how to route the final number as well, right? To be the proper or correct number of sig fig. Okay, so the rule that I'm going to just give to you is going to be anything that is between 0 to 4, you round down. Anything 5 and up, you round up. Okay, so that might be like odd even number. When you deal with 5, those are things that I don't care. It's too much. Okay, so I just want to keep it simple for you here. Okay, so just know that 5 and above round up, 4 and below round down. Okay, so note that when you round, okay, so when you round number, you have to only round the final answer. You do not do rounding each of the step, okay, because it's end up adding error to each of those. Okay, so you are going to end up obtaining the incorrect answer. Okay, so just know that when you round, it's going to be only for the final answer. So I would like you to actually skip to DIY problem number 2 first before we get into the calculations. Okay, so in this case, I want to go over how you can report the final answer with a certain number of sig fig. Okay, so if the problem asks you, for example, to report the number with just 2 sig fig, what do you do? Right. So in this case, if you're looking at this number 517, okay, so this contains 3 sig fig. So somehow we need to report this into sig fig. Some of you might be like, oh, I just cut this out, right? So I'm going to report it as 52. The answer is no. The reason for that is because the value that is given, 517, is not equal to 52. Right? So if you think about money, you have $500 is not going to equal to $50. You know what I mean? So therefore, you can't just cut out a number. Okay, so in this case, you need to first report this number in scientific notation. So I'm going to report this as 5.17, okay, times 10 to positive 2, right? Because it is a big value, right? So you move decimal to be after 5. So therefore, in this case, it's going to be a big number. So it makes sense, right? Because if you think about this, right? So this number right here, 517, is the same as 5.17 multiplied by 100, right? So it's going to give you the same identical value. So that means you did not cut anything. You still, the meaning of this value is still going to be the same. Okay, so the next thing is, because when we count a sig fig, we don't care about the notation. So therefore, in this case, you are dealing with only the number before the notation, right? So in this case, if I want to sig fig, so this 1, this is 2, so I'm going to cut here. Okay, if I cut here, the last digit is 7, right? So we already learned, right? So if it's 5 and above, you round up, right? So that means in this case, you are going to round this to 5.2 times 10 to second. So in this case, this number is still going to give the same value as this original number. Okay. Now, what about the second one? Well, the second one, we have decimal place here. We want 2 sig fig, right? So in this case, I'm just gonna, is it okay if I cut here? Okay, so if I cut here, you see the number that we are going to cut, right? This is 3. You are going to round down because between 0 to 4, right? So therefore, in this case, the number would be 86. Now check your answer first. If I round this down and the report number of 2 sig fig would be 86, is it similar to 86 what we have here? The answer is yes. So that means it's good. You don't have to actually convert it to scientific notation in this case. Okay. The next one. Okay, so the next one we want 2 sig fig. So 1, 2. So I'm gonna cut right here. So the digit after 3, right? So this one right here is 8. So 8 is between 5 and 9, so you're going to round it up, right? So therefore, the number that you're going to report would be 6.4 times 10 to the third. Okay, so still give you the same value, right? So 6.382 times 1,000, 6.4 times 1,000, right? So it's about the same. All right, let's pause the video now and complete these 3 numbers and report them into sig fig. Okay, so once you finish, then you can actually resume the video again to check your answer. All right, let's check your work together. So these are the answer. Okay, so if you get the different answer, please again, do not hesitate to reach out to me, okay? Okay, so the next thing we are going to take a look at sig fig in calculation. So as I mentioned before, okay, so in this case, I'm going to take a look at multiplication and division first, and I'm going to look at addition and subtraction. Okay, so I'm going to divide this. Okay, so right here. Okay, so when you deal with multiplication or division, you are going to go with the fewest number of sig fig. Okay, so for example, the given number that you see here, this contains 4 sig fig, this contains 2 sig fig. Therefore, your final answer should contain 2 sig fig. Okay, so your final answer have to have 2 sig fig. This one has 5 sig fig. This one contains only 3 sig fig. So therefore, the least number of sig fig will determine your sig fig in your final answer. So therefore, your final answer should contain only 3 sig fig. Okay, so that's how I deal with this. What about the addition and subtraction then? So subtraction and addition are going to go by the fewest number of decimal place. So you are going to count the number of decimal places, not the sig fig. Okay, so in this case, the number of decimal places for this number would be 1, 2. This is 2 decimal places. Okay, so this one contains just 1. So therefore, your final answer should contain only 1 decimal place. Okay, so same thing for subtraction as well. Subtraction contains 1, 2, so 2 decimal place for this number, and this is 1 decimal for this second number. So total, your final answer going to be limited by 1 decimal place. So now let's go back to the first calculation. Okay, so this one right here. So if you calculate this, you need to report your answer with 2 sig fig, so it would be 3.0. If you calculate this, right, so you are going to report your answer with 3 sig fig, so it would be either 518 or 5. So you can do both, right? So this one already contains 3 sig fig. These are also 3 sig fig as well, so any of those would work. Next one, right? So when you subtract those, you are going to get 1 decimal place. Okay, so therefore your final answer should just going to contain that. Okay, so with subtraction here, you are going to get 7.45, right? So if you subtract these two numbers, but we want it to be only 1 decimal place, so therefore you are going to cut right here, right, and report with just 1 decimal place. So therefore your final answer would be 7.5. Okay. Now, what about the calculation that involved with several operations? Okay, so this one you are going to need to follow the order of operation. Okay, so the first one, right? So you are going to do those operation within the parentheses first, right? Before you like do the rest. Okay, so I'm going to looking at this. Okay, so I'm going to go ahead calculate the first part and then the second part before I add them together. Okay, so that's what my plan would be. Okay, so if I calculate the top part, that's what would be the number. Okay, so this one right here, you are going to underline this number with the correct sig fig, but you don't round them. Okay, so we're not doing any rounding yet. I'm just gonna underline to keep track of it. Okay, so because we have 3 sig fig here, we have 4 sig fig here, so this going to be only 3 sig fig, right? So again, I'm not going to cut it yet, right? So I'm going to underline that so that, okay, this is 3 sig fig. Okay, so this 3 sig fig would carry on for the final answer. Now if you do 1.9 minus 0.005, this is the number that comes from that calculation. So in this case, you see that we deal with subtraction. We are going to go by the number of decimal place. Okay, so this one contains 1 decimal place. This one contains 2 decimal place. So therefore, your answer is going to contain only 1. Okay, so I'm going to again underline it. I'm not going to round it yet. So again, the number of sig fig that come from the first operation would be 3 sig fig, and the number of sig fig that come from the second operation would be 2 sig fig, but 1 decimal place. The reason why we're going off by decimal place because it's subtraction. Okay, so now the last one we are going to do is going to be addition, right? So this addition right here. Okay, so we are going to pretty much add these two together. So if you add these two together, this is the number that is given. Okay, so now in order to determine the number of sig fig in your final answer, what you are going to go off is going to be the whatever operation that you do last. Okay, so in this case, we did addition last. So that means going to go by the number of decimal place. Okay, so remember the first operation giving us 3 sig fig. If we're looking at this number that we underline right here, that would be 3 sig fig. But if you're looking at the number of decimal place, right, so these 3 sig fig contain 2 decimal places. So now the second operation, right, so you will see that this value right here is limited by number of decimal place, so it's contain only 1. Or if you want to count number of sig fig, this would be 2 sig fig. right? Because 1 and 3, there are 2 of them, but the last operation is addition. So therefore, addition will go by the least number of decimal place. So the least of number of decimal place would be 1 decimal place that come from the prior operation, which is subtraction. So therefore, your final answer would contain only 1 decimal place, which is going to be this. Right? So that's 1 decimal place right there. So you are going to cut right here. Right? So your final answer would be reported as 9.9. Okay, so because limited by the last operation we did there with the addition. All right, I'm going to let you do number 3 yourself. However, I'm going to go over some of the things that you will need to know. Okay, so whenever that you see number 1 like this, that written in the fractional form like this one right here is kind of like a placeholder, because if you think about it, right, it's a division, right, it's a divide. So that means you can, this one right here is the exact number. Okay, so you don't count this toward number of sig fig. Okay, so this is not part of the number of sig fig. Okay, so it's similar to if you were replace this with divide, right, by 6.314 times 10 to negative 34, right? It's the same thing. So that means in this case, that one right there will not be count toward number of sig fig in your final answer. Okay, so note that. Same thing as well if you will ever do a fractional form where 1 on the bottom. Okay, so that one right there will not be part of sig fig either, because that is just the exact number. It's kind of like a placeholder right there. Okay. All right, so I would like you to complete this yourself and then check your answer against mine. Okay, so pause the video now and complete all of this. Now let's check your answer. Okay, so these are the answer. Okay, so if your answer come out to be different from what I have here, just make sure that you reach out to me. Okay, so that way we are certain that you actually understand this before you move to the next topic. All right, last but not least for this section of 1.4 is going to be accuracy versus precision, because when you're moving toward 122 and 123 or more advanced chemistry, you are going to definitely have to deal with measurements, right? And then all measurement will come with number, unit, uncertainty, and also accuracy and also precision as well. Okay, so the difference between these two would be accuracy would tell you how close you are to the true value, right? So if you run the experiment, right, how close is that value to the known value or to the literature value? Precision would be how close your data to each other, right? So when you replicate them, right, so how close those values are together. For example, if you use target analogy right here, right, so good accuracy and good precision would be, right, so right at the target, right, so that would be very good accuracy, and all of your data are grouped together within that region as well. That would be good precision as well. Good accuracy, poor precision would be scattered data, but some of your data also right at the mark or right at the target as well. Okay, so poor accuracy but good precision would be is way off from the known or true value, but your data are grouped close together, right? So this one will have to deal with like errors that we're gonna learn when you take Chem Lab the next term, okay? And then poor accuracy and poor precision would be all over the place. So for example, given here on table 1.5, okay, so it's giving you the volume that measure from 3 different dispensers. Okay, so dispenser 1, 2, and 3. Okay, so it's give you different volume. And it's tell us that it need to deliver by 10 ounce or 296 milliliters. So that means the true value or the target that we are looking at is 296 milliliter. So the first dispenser, you probably notice that the value is way off from 296 milliliter, but they all close together, right? So this is an example of poor accuracy, but good precision. Now I'm going to skip to dispenser 3 real quick. Okay, so if you're looking at dispenser 3, okay, so all of those are very close to 296. So this would be an example of good accuracy, and also they are very close to each other as well. So it's going to be good precision as well. And dispensers 2, if you think about this, right, so they seem to be scattered, and some of them are close to the known value and some of them not. But if you find out the average, it's turned out the average come to be very close to the true value. So this is an example of good accuracy but poor precision. Okay, so when the average get close to the true value. So that means when you're doing the experiment, right, you probably have to conduct several trials or multiple times, right, to get the number. And when you get the average, sometimes the average will average out the error, right? So somehow we'll get close to the true value. Now I would like you to complete this one yourself. Okay, so I would like you to go ahead find out which data are accurate or precise or both or neither, right? So let's pause the video now and then complete this and then resume the video again when you finish. Let's check the first one together. So the first one is neither. So we actually don't know the true value. So that means we don't know if it's accurate or not, right? So, but for sure it's not precise. The second one is precise but not accurate because the true value that we are shooting for is 25, right? So 25 milliliter of the pipette. And the last one, you probably notice that they are very close to each other and is almost to the 100% of the purity as well. So therefore, this data is both precise and accurate. So here's a summary of chapter 1.4. Right? So you learn about the numbers and also unit as well, and plus the uncertainty that come with the measurement as well. Okay, so you should be able to start doing homework chapter 1.4 now. Okay, so start that as soon as possible, okay, before you move to the next chapter lesson.